Engineering teams spend weeks running exhaustive cost optimization sprints. They right-size compute instances, kill zombie resources, and renegotiate reserve capacity. But when the monthly cloud bill arrives, infrastructure costs are still outpacing revenue growth. We tend to look at the massive scale of the physical hardware and assume the costs are tied to the metal. But the real financial leakage is happening inside the routing logic. Executive dashboards consistently miss the largest source of capital waste because they measure compute instances. They track what is running, not how the data is traveling. This massive financial drain comes down to two specific design choices: routing every decision back to a centralized origin and fragmenting the network across multiple single-purpose vendors. Capital waste at this scale is a direct consequence of bloated architectural design. In the 1960s, the industrial designer Dieter Rams built a philosophy around a very specific engineering principle: less but better. Rams applied relentless reduction to complex consumer hardware. He stripped away every non-essential component, leaving only the exact mechanisms required for the machine to function. We can apply this exact logic to cloud network topology. By stripping away non-essential routing hops and moving execution to a unified network perimeter, you eliminate the operational friction that quietly destroys profit margins. A minimalist edge-native design directly increases bottom-line profit by structurally forcing a reduction in latency and data transit. This diagram shows a centralized origin server. In a standard architecture, this is where all the heavy lifting happens. Take a high-frequency, lightweight request like bot classification. The request originates at the user's device, travels across the geographic network to the origin to be categorized, and is sent all the way back. Every byte that leaves that origin pays a toll. These compounding cross-net add up, typically consuming 10 to 15% of an enterprise cloud bill just for routine logic. For data-intensive workloads, that financial penalty scales aggressively, eating up to 40% of the total infrastructure budget. Then there is the cost of compute capacity itself, heavily driven by the illusion of cloud autoscaling. The theory is that servers spin up precisely when needed, but during a sudden viral event or massive bot surge, the mechanical reaction time of an origin server is too slow to catch the wave. This graph tracks traffic volume against server capacity. The traffic hits instantly, while the origin autoscaler begins provisioning new instances minutes later, after the spike has already peaked. To compensate for this delay, engineering teams are forced to over-provision. They leave between 30 and 65% of paid cluster resources completely idle, permanently paying for headroom they rarely use. Centralized architectures charge the enterprise twice: constant egress tolls for data transit, and massive premiums for idle server capacity kept warm just in case. The industry consensus suggests that combining specialized single-purpose vendors is the safest way to manage scale. The architectural map quickly expands. You add a CDN, a separate bot management tool, and a third-party AI inference platform. A single user action now bounces across all these disparate systems before a response is generated. Every intersection between two different vendors extracts an architectural tax. These are the seams of the network. When a request hops from your CDN to your AI inference platform, it triggers fresh cross-vendor transit fees. More importantly, it leaves the provider's private backbone and traverses the public internet, adding severe latency. The financial cost is only half the equation. The other half is the developer tax. Maintaining a multi-vendor, multi-region environment forces engineers away from building products. They spend their hours writing complex integration glue, syncing configurations, and running distributed debugging across entirely different platforms. Stacking vendors does not increase operational redundancy. It degrades application performance and inflates engineering overhead. The operational fix requires a strict reduction of these network boundaries. You strip away the bloat. You collapse the fragmented single-purpose tools into one unified compute perimeter at the edge. By executing authentication and personalization logic directly on this perimeter, latency drops from 200 milliseconds down to 40 milliseconds. Unified networks, combining edge workers with serverless infrastructure like Akamai sanctions, process this logic without triggering cross-vendor transit fees. The egress cost for these decisions drops to zero. The impact extends to advanced compute. Running AI product recommendations natively on a connected edge platform reduces inference costs by 86%. Data moves cleanly when it never leaves the network backbone. Shifting execution to a unified edge structurally re-engineers the request lifecycle. It prevents the origin round trip and eliminates compounding vendor fees entirely. Under heavy traffic, the contrast is stark. The fragmented stack buckles under its own complexity, bleeding capital at every seam. The minimal stack absorbs the load efficiently at the perimeter. This simplifies the operational reality for the engineering team. Agonizing region-by-region container rollouts are replaced with single command code deployments across the entire global network. To the technical leaders managing these systems, idle cloud capacity and constant integration overhead are not inevitable costs of doing business. They are structural design flaws. This is the blueprint for network efficiency. It relies on strict geometric order and functional clarity. True engineering sophistication is rarely found in stacking more specialized services on top of a fragile foundation. It is found in absolute functional clarity. Stripping away non-essential boundaries and decentralizing logic is the definitive way to scale a network globally while protecting your profit margins.